what we previously did was do a Bayesian classifier, and then we converted it into a semi-supervised learning algorithm by having a few label samples. So what we're going to do now is to try to build completely unsupervised learning algorithms. So specifically, we look at what are called as Gaussian mixture models. So we have a couple of Gaussians, and we'll have a bunch of random samples from those Gaussians. And given those data points without the labels, what we'll try to do is try to classify it into the two different Gaussians. So if we are theoretically able to do that without using the labels, then this is an example of an unsupervised learning algorithm. This is just a toy example, just to give a flavor of how these methods converge. And like I previously mentioned in the previous lectures, these methods only work if the data is fairly clean in some sense. So let's go and try to implement a simple Gaussian mixture model and an expectation maximization algorithm that we saw on the mixture model. Okay, so so this is going to be a Python code from scratch, like last time, and let's take a quick look at it. So what we're going to do is first try to see if we can generate a bunch of samples. So I'm going to call the first argument as op. This is again just fast code, so it might not be the cleanest or the best code, but let's just try to do this. So let's call this generate, and if I want to generate, I'm just going to generate a bunch of samples. This is going to be our input file when we are trying to learn the classifier. So I'm just simply going to have two Gaussians and print a bunch of values sampled from those Gaussians. So let's say I have 100 data points from the first Gaussian, and then I just looked it up. Random.gauss gives a sample from a Gaussian distribution. So we have a random Gaussian, and then 0 is the label. We'll just use the label for, I guess, if we want to do accuracy. So, and then I'm going to have 10 samples. So it's going to have different priors. So one is going to be 10 times as big as the other Gaussian. We'll have a well-separated Gaussian. So these two basically don't even overlap much, or if at all overlap, because the standard deviation of each one is like 1, so they shouldn't really overlap. So it should be fairly easy for us to tell the two Gaussians apart. Then I need to import random to get my Gaussian, and I think we might be done. So let's give this a shot. Sounds about right. So the first bunch of points are distributed around 0, and the last 10 points are distributed around 5 with a standard deviation of about 1. So let's store this in a data file and then go back to our code. So what we want to do now is literally take these Gaussians and try to cluster them basically. All right, so if I don't have to generate data points, then we are going to now run our EM algorithm. So note that the model here contains, so last time we needed the word frequencies and the priors. What we're going to need this time to define a distribution, the model, is a prior the mean of the Gaussian and the standard deviation of the Gaussian. That defines one of the two clusters in a sense. Okay, so let's start with the correct values. So my priors are going to be something like, for my 0 distribution, it's going to have you know, a 9 or 10 times the value, and for my 1 distribution, we're going to have something like that. It's probably not exactly right, but something along those lines. It doesn't have to be very precise. So priors is about 0.9 and 0.1. In effect, I think it should be a little bit more than that biased, but it's okay. And then the means that we need are, the correct means are 0 and 5. And the correct standard deviations are are 1 and 1. Okay, and then basically we're just going to run our EM algorithm. So let's just start with one iteration. And what we're going to do is, my file name is going to be sys.argv of 2. I guess this only happens when we don't generate something, so it goes in there. Again, this is not the cleanest of code, but it's just quick code for now. Split for L in something like that. So we get the list of all the lines, and like last time, what we're going to do is we're going to have this thing called p lines, which contains both the posterior probability for that specific sample and the data points themselves. Okay, so this is just convenient for us to do a relearn step like we did for the Bayesian classifier on text documents. Okay, so we're now going to go through all the lines. And actually, let me just first try to do the posterior. So I would do a get posterior of so that's basically my sampled point, and I send with it priors, means, standard deviations, and let me print the posterior. So basically that should the posterior should be for the first set of points, it should be highly biased towards 0, and the last set of points, it should basically be biased towards 1. So let's go ahead and implement the get posterior method. This method is going to take some value x, the priors, the means, and the standard deviations. Okay, and let's see. So basically, I guess I haven't imported the counter. So let me do that from collections, import counter. We needed that for the priors, and we will need that back again here because my posterior is also going to be a counter. Okay, and now what we're going to do is, this is very, very similar template to our previous code, but we're going to go through all the keys, and then we're just going to compute the posterior. Now at this point, the posterior is within only a constant factors, but what it's going to be is, it's going to be the likelihood. The likelihood here is just the density of the Gaussian, so it's going to be the density of x given the mean, standard deviation, multiplied, just like last time, the prior. Okay. And the posterior has a denominator for it to be a probability, but what we're going to do is, since it's a constant, we will just, like last time, sort of normalize it with the sum of the rest of the posterior. So just going to do sum posteriors equals sum of posteriors dot values, and then just divide it so that we have a probability. All right, so let's see. Let's try to figure out what the density is going to be. So density, it's going to take a mean, a standard deviation, and we're going to come up with a density. Let's call this S and M for concise, for being concise, and we're going to return 1 over, I could get this wrong, but I think it's 1 over sigma, something like sigma square root 2 pi times e to the negative x minus mu whole squared divided by 2 times sigma squared, something like that, I think. Could get it wrong, but I think something like that should work. Okay, so that should be the density. So let's see if we are done here. So for the posterior, we just needed the density and then some posterior. I think we're close to done here, at least with printing the posteriors as it is. So let's give it a shot. Gaussian EM. We're going to need the data file, and the first argument was generate, so it's basically not generate, can be anything, something like that. Okay. Okay. Oh, we did not return the posteriors. That looks kind of right. So weirdly enough, this point is classified as a 0 at the end. Let's look at the data file. I guess that's that point. So it was a little bit kind of maybe overlapping after all. So it's classifying 2.3 as a 0 bucket rather than a 1 bucket. But nevertheless, mostly it looks kind of right because the initial set of posteriors are heavily biased towards 0. The later set of posteriors are biased towards 1. So that looks right. Cool. So we're inching closer. So let's go back to what we intended to do, which was in P lines here, we wanted to append the posterior along with the line itself. So that's that. Okay. And then what we want to do is we want to relearn. So this would process all the lines. And after we process all the lines, we want to relearn using p-lines and get a new estimate for the priors, means, and the standard deviations. So let's try to do that. So relearn is going to take just a set of p-lines. It's going to come up with the new priors, new means, and new standard deviations. Okay, so what we're going to do, this is very similar in template sort of structure as last time. It's going to go through the posteriors, along with all the lines, and then it's going to go through the set of all the classes, which is the two distributions we have. Then we're just going to do priors plus equals posterior of k. Note that this would have been plus equals 1 if we knew that classification. So the posterior of k is literally just going to do almost in this case, since it's so heavily biased, it's going to be like plus equals 1 on the 1 class and plus equals 1 on the 0 class, depending on which way the sample got classified, which way the line got classified. But it's a soft classification like we saw last time. So, and the means of k is going to be weighted by the posterior. So it's going to be posterior of k times something like that. And the standard deviations, we will figure it out, but I'm just going to do e of x squared first. So I'm just going to do squared of each number, and we can later sort of convert it into a standard deviation. So something like that should be it. Okay, so let's see. So, and then here we are going to say, we're going to have to normalize this. So we're going to have sum priors equals sum of the priors dot values, and then for k in priors dot keys, we're just going to have to renormalize it. But before that, let's normalize our mean, because we're going to have to divide that by. So note that I can actually divide this by priors of k. What I'm done here is I want to divide it by sum of all these posteriors, because that's going to be, I think, the average of the weighted numbers. So that's means of k. Standard deviations is going to be a little bit more tricky. But first, let me get e of x squared. So that would just be that. Now I have e of x squared. Now for my standard deviation, I just do e of x squared minus e of x the whole squared. Okay, something like that. And then I need a square root, because this is my variance, and I have a square root, and I have e of x squared minus e of x the whole squared. And then let's normalize our priors now with some priors. Okay, that should be it. I think. So I think we are almost done. So let's return priors, means, and standard deviations. And we are in good shape, I think. So now what we can do is, actually, even before we learn, since we didn't print this out, let's print the priors, means, and then print the standard deviations. Okay. Let's increase this to 2, so it'll actually print one iteration at least. I think let's give it a shot. We probably missed something, but we'll patch it up. Gaussian EM data 1. I need that not generate. I think this should be posterior. All right, so we started off with a 0.9.1. It should hopefully stay roughly there, which it did. And the mean should stay roughly at the same thing, which is a 5 and a 0, which it kind of did. And the standard deviation should stay at 1, which it kind of did. Now, basically, even if we increase the iterations, it should not diverge too much, or at least that's the idea. So let's increase this to 10 iterations. Let's do print. All right, let's give this a run now. Okay, so we have about 10 iterations, and roughly my priors have stayed the same. Means have roughly stayed the same, 5 and 0, and the standard deviations have roughly stayed the same. So that's a good sign. That means that if we started off with the right values, it kind of goes nowhere. Ideally, it shouldn't. Let's increase the iterations even further. 100 iterations, and basically, it's kind of 5.3, 0, and 1. Okay, so that's a good sign. Now let's change our starting value. That's basically the cool part, right? So let's say that my priors was 0.5, 0.5. And let's see if it converges to the right values, okay? So I start off with 0.5, 0.5. In one iteration, it pretty much goes to the right values, which is pretty cool. Within a single iteration, we basically get 0.9 and essentially 0.09, which is what we want to see. And we get 5 and 0 and a standard deviation of 1. Just one single iteration is all that we needed. 0.5, 0.5 would be your kind of default prior. So even if you give it the default prior, it does the right thing. As for the means, let's try something. So we can't do 2.5, 2.5. We need to bias it a little bit one way or another. So let's bias it towards 2 and 3. Okay. So in a single iteration, it went to 0.8, 0.1 or 0.8, 0.2, and a 2.7 mean, which is not quite the right mean, obviously, and a 0, which is close to the right mean. And the standard deviations are a little bit off. So even, in fact, after 10 iterations, I think the priors converge to the right values, the means converge to the right values. Standard deviations are a little bit off, but I guess it's not too bad. We can try increasing the iterations to see if somehow some points were misclassified. Okay, so it's much better. So within we can even see when it started converging to the right values. So about iteration 10, it's still in the wrong standard deviations. And about, I think, in iteration 17, or I think we are basically down to the correct 0.9, 0.08, which is not too bad. 5 and 0 means, and a standard deviation of about 1, which is great. This is exactly what we wanted to see. Now in practice, what we would do would be, this would be something like math.random and hope that it still kind of works, because you don't even need to figure out what to do. So math.random, I don't even know what the standard deviation is. I'm just going to randomly guess a standard deviation. I don't even know what the mean is. I'm going to guess a random mean. And priors, I'm just going to leave it at 50-50 priors, and let's see what happens. I guess it's not math.random. It's random.random. Okay, so here we go. Let's go up to see what happened. 0.5, 0.5. So the means initially was 0.5, 0.2, and standard deviations was 0.85 and 0.6. One iteration, the mean hasn't changed much. But you slowly see that it's starting to go up on one side. 0.7, 0.2, 0.9, and as the iterations increase, it's 1.8. Goes up by iteration 24. It's at 3.4 and 0.01, which is what we want to see. And about iteration 31, it's at 4.5 to 4.8 and 0. That's what we want to see. And by 40th iteration, it's basically converged to what we want to see, which is a 0.9, 0.07, 5, and 0 mean, and a standard deviation of 1 and 1. So that's the beauty of it. So at this point, basically, it's converged to the two correct distributions, which means it's also doing a good job with the classification, just as well as doing a good job with finding the two distributions themselves. So it's classifying correctly, converging to the right distribution. And obviously, it doesn't go astray once it's in the right distribution. It kind of stays in the right distribution, as we originally saw. We can even tweak our generation a little bit and kind of hope for the best. So this was a well-separated distribution. We can even make it less separated. So we could sort of make this 2 and standard deviation of, let's do standard deviation of 2 and standard deviation of 1, just so that we can see it converging to different standard deviations. And let's see how it does that. So I would need to regenerate the data. So this is going to be, I think, generate, and then I'm going to put it into a new file. Let's take a look at the file. That's kind of how the file looks. And you can kind of see that the 0 distribution has some large numbers. In fact, it has numbers very close to the 1 distribution. So let's now run this guy over the whole data. Cool, you can sort of see that now it's kind of having some trouble. Even after 100 iterations, the priors are not too bad, but you can see that the means, it's kind of struggling a little bit to get the right convergence. We could try to seed it more closely to the right values. Even if we seed it to the right values, it does diverge a little bit, just to be expected, because at this point the distribution is a little bit on the closer side, that it's actually getting hard to distinguish the two clusters effectively. But at least you can now see that it got the standard deviation right. It got the standard deviation of 2 and a standard deviation of closer to 1.5. Not as good as we would want, but I guess it's not too shabby. We can also try to increase. One thing we can try to do is, let's try to increase our number of data points. So we only had 10 points, right? That's pretty noisy. So it's 1,000 and 100 this time. And let's see if that's enough to make the difference. It's going to be data 3. Okay, it's 1,100. So let's go back now and make these guys random.random, make it hard, see if it does the right thing. Still kind of having some amount of trouble now. So at least now it sort of converges to the right distribution, which is good. It's 0.9, or it stays in the right distribution, which was 5 and 0, and then 2 and 1, which is encouraging. So the other thing we could try to do is go back to random.random and try to see if we need more iterations. I would be surprised if we need like 1,000 iterations, but who knows. Actually, it is converging. That's awesome. So basically now you can see that it is going closer and closer to 5. It's kind of converged at this point, but it is cool that it actually took significantly longer for it to get to the right distribution, but it's very cool that it got to the right distribution. Let's go up to see when it started converging. So you can see that iteration 70 is still very far from the final distribution, and even in iteration 150, it's still in a mean of 2.9 and 0. But you can see sort of slowly it is inching towards the 5 mean, and eventually it gets at about I guess right around there. So about 250 iterations, and then it got to the 0.9 and 0.09, which is correct. Those are the correct priors. 4.84, which is fine because the sample mean is going to be a little bit different. But 4.84 and 0 is pretty good. 1.96 and 0.9 is also pretty good. Those are the two standard deviations. So that's basically EM algorithm on a Gaussian mixture model. You might need more data points. You might need more iterations. You might have to have, if obviously the clusters are well separated, then you need very few data points. But if the clusters are not that well separated, then obviously you need more data points to have basically the ability to distinguish the two clusters.